Have you ever looked up at the night sky and wondered about the vastness of space? The universe is an awe-inspiring expanse that stretches beyond our imagination. Space is like a giant playground where stars are born, galaxies collide, and cosmic events unfold in a spectacular dance. Planets orbit their suns in a delicate balance, creating a mesmerizing ballet of celestial bodies. Just like our universe has rules that govern its behavior, scientists and mathematicians have discovered patterns and principles that explain these cosmic phenomena. Mathematicians have created special spaces with their own set of rules, known as vector spaces. These spaces help us understand and describe the world around us in a structured way. These spaces are called vector spaces, and they're like playgrounds for special arrows called vectors. Vectors are fundamental tools in mathematics and physics, representing quantities that have both magnitude and direction. Imagine vectors as arrows that can point in any direction and have a certain length. They can be added together, scaled, and manipulated according to specific rules. In this grand cosmic adventure, we'll explore how vectors and vector spaces help us make sense of the universe. From the smallest particles to the largest galaxies, vectors play a crucial role in our understanding of the cosmos. We'll journey through the exciting world of vector spaces, discovering how they are used in various fields such as physics, engineering, and computer science. Don't worry, it won't be a boring math lecture. We'll use fun examples and easy-to-understand language to make the concepts clear and engaging. Get ready to explore the wonders of vector spaces. Together, we'll unlock the secrets of these mathematical playgrounds and see how they connect to the universe we live in.
Imagine a vast, empty playground. This playground is our vector space. It's not your ordinary playground with swings and slides. It's a special mathematical playground where we play with arrows called vectors. These vectors can be long or short, pointing in any direction. We can add them together, stretch them, or shrink them. But there's a catch. No matter what we do, the result must always stay inside the playground. That's one of the fundamental rules of vector spaces.
Vectors are like arrows that have both a size and a direction. Think of an arrow pointing from Earth to the moon. The length of the arrow tells us the distance between the two, and the direction tells us which way to go. In our vector space playground, vectors can represent anything that has both magnitude and direction. For example, they can represent the velocity of a spaceship, the force of gravity, or even the displacement of a curious robot exploring a new planet.
Now, imagine you have a magic wand that can stretch or shrink our cosmic arrows. This magic wand is called a scalar. Scalars are just numbers, and they can make our vectors longer or shorter. For example, if we multiply a vector by 2, it will become twice as long. If we multiply it by 1/2, it will shrink to half its size. Scalars are like the volume control for our vectors.
Section 5. Axiom 1. Closure under addition. Staying inside the playground. Remember our playground rule? No matter what we do, the result must always stay inside the playground. This brings us to our first axiom, closure under addition. An axiom is like a ground rule. This axiom says that if we add any two vectors in our vector space, the resulting vector must also be inside the same vector space. It's like combining two arrows in our playground. The new arrow will still be within the playground boundaries. Section 6. Axiom 2. Closure under scalar multiplication. Still playing in the same playground. Our second axiom, closure under scalar multiplication, is similar to the first one. It's a fundamental concept in linear algebra and vector spaces. It states that if we multiply any vector in our vector space by a scalar, the resulting vector must also stay inside the same vector space. This means that no matter how we scale our vector, whether we make it longer or shorter, it will always remain within the confines of our defined space. This axiom ensures that our arrows, even when stretched or shrunk, remain within the boundaries of our vector space playground. Imagine you have a magical playground where the boundaries are set, and no matter how you change the size of your arrows, they never leave this magical space. It's like using our magic wand on an arrow. No matter how much we stretch or shrink it, it will always stay inside the playground. This concept is crucial because it maintains the integrity of our vector space. It allows us to perform operations without worrying about stepping outside the boundaries. So, whether we are dealing with tiny vectors or gigantic ones, as long as we are multiplying by a scalar, we are still playing in the same playground. This consistency is what makes vector spaces so reliable and predictable in mathematics. Understanding closure under scalar multiplication helps us appreciate the structure and rules that govern vector spaces. It's like knowing the rules of a game. Once you understand them, you can play confidently and creatively within those rules. So remember, in our vector space playground, our arrows can change size, but they will always stay within the magical boundaries we've set. This axiom is a cornerstone of linear algebra, providing a foundation for more complex concepts and operations. By mastering it, we ensure that we can navigate the world of vectors with ease and precision. So let's keep exploring and playing in our vector space playground, knowing that our arrows, no matter how they change, will always stay within the boundaries.
Section 7, Chie. Axiom 3. The zero vector, the center of our playground. Every playground has a center, and our vector space playground is no exception. The zero vector is the center of our playground, and it's a special vector that has zero length and no direction. Think of it as a dot in the middle of our playground. Adding the zero vector to any other vector doesn't change the other vector's direction or size. It's like adding nothing at all.
Section 8. More axioms, the rules of the playground. Our vector space playground has a few more axioms, just like any other playground has rules to keep things fun and organized. These axioms ensure that our vectors always behave in a predictable and consistent way. We won't go into detail about all the axioms, but just know that they are essential for maintaining order in our vector space playground and ensuring that our mathematical games always make sense.
Section 9. Properties of vector spaces. Fun things we can do. Now that we understand the basic rules of our vector space playground, let's explore some fun things we can do with vectors. We can add them, subtract them, and even combine them in various ways. These properties make vector spaces incredibly useful for solving real-world problems. For example, engineers use vectors to design bridges and buildings. Physicists use them to study the motion of objects. And computer scientists use them to create realistic graphics and animations.
Section 10. Why are vector spaces important? Beyond the playground. Imagine a world where every point, every direction, and every force can be described with precision and clarity. That's the magic of vector spaces. Our journey through the world of vector spaces has come to an end, but this is just the beginning of understanding their significance. These mathematical constructs are the backbone of many scientific and engineering feats. But the adventure doesn't stop here. The principles of vector spaces extend far beyond the classroom, influencing various aspects of our daily lives and the world at large. Vector spaces are not just abstract mathematical concepts. They are foundational tools used in physics to describe forces and motion, in computer science for graphics and data analysis, and in engineering for structural design. They have real-world applications in various fields. For instance, in aerospace engineering, vector spaces help in plotting the trajectory of spacecraft, ensuring they reach their destinations accurately. Just like our universe is full of wonder and complexity, vector spaces provide a framework to navigate and make sense of this complexity. They allow us to model and solve problems that would otherwise be insurmountable. Vector spaces offer a powerful tool for understanding and describing the world around us. From the design of bridges and buildings to the development of new technologies, vector spaces are integral to innovation and progress. As we continue to explore the cosmos of knowledge, vector spaces will undoubtedly play a crucial role in shaping our understanding of the universe and beyond. They are the language through which we can decode the mysteries of the cosmos. Vector spaces will undoubtedly play a crucial role in shaping our understanding of the universe and beyond. Whether it's in the realm of quantum mechanics, where they help describe the behavior of particles, or in the field of artificial intelligence, where they assist in processing complex data, vector spaces are indispensable. The adventure of learning and applying vector spaces is a journey that continues to unfold, offering endless possibilities for discovery and innovation.